Welcome. This video will go over some worked examples to selected NCEES type questions related to the FE civil exam in the topic of hydraulics and hydrology. And specifically, there'll be hydrology. There's 5 questions. Hydraulics. Five questions, and then groundwater. I guess it's hydrology and hydraulics all in one. 5 questions. I'm going to simulate the exam on a server in a learning management system called Moodle. It's similar to Blackboard. If you look at the top, you'll notice that it's a part of another class. That's coincidental. It was simply easier to hide the material within an existing course rather than go through the trouble to create an entirely new one. And that's more of a system administrator issue and not so much a viewer issue. Remember, this is a video, so it can be paused, it can be scrolled backward, it can be moved forward, and you can use that capability to your benefit as you study for the FE Civil. The materials here are based largely on those by Lindeburg. I think that's the correct spelling. There's an FE review manual. And there's an FE civil manual. Couple of prerequisites that are important is the NCEES supplied reference. Which I'll show you in a second, my copy, and you'll need a calculator. I was originally tempted to pull up an Excel spreadsheet and use that as a calculator, but I have a feeling that that's not permitted, so I'll do it the old-fashioned, well, a sort of old-fashioned way. It's not like I'm using an abacus or a slide rule or something that does actual computation. So those are what I believe you're allowed on the exam itself, and of course the computer that you're logged in at. As necessary in this review, I may shell out to supporting materials. Those would not be available to you on an exam. So first, the supplied reference. I have my copy right here, and you'll find the search and destroy feature very useful as you work through either the real exam or the training. The other tool we need is a calculator. Let me get one of those up and running. Calculator, and that looks like a scientific one, so that should be fairly representative of what you would have on an exam, and I'll kind of keep it in the corner, sort of keep it out of the way. Okay, work I do by hand will be shown here in this right screen. Scrolling the handbook, I'll try to keep to the left side of it. I use this scrolling feature here and here. And the simulated quiz is right here. So let's go ahead and begin. Our first question is, 2 adjacent fields contribute runoff to a collector. Field 1 is 2 acres with a runoff coefficient of 0.35. Field 2 is 4 acres with a runoff coefficient of 0.65. rainfall intensity is given as 3.9 inches per hour, and we've been told that this is at the time to concentration. So, if we don't know what we're doing, let's go ahead and see what keywords we have in the problem statement. We have runoff, collector, runoff coefficient. Let's go ahead and use that as a search item. So I'm copying that, pasting, and it brings us up to the rational formula. The rational formula is Q discharge is equal to the Culinary Institute of America, CIA. Well, since both these fields drain to the same collector, we have an option. We could try for a composite runoff coefficient, or we can calculate the flow from field 1, the flow from field 2, and add them together. I'm going to try that first. So we have QP from field 1 is equal to 0.35 times 3.9 inches per hour times 2 acres, which will equal something. And QP2 is equal to 0.65 times 3.9 inches per hour times 4 acres. That will equal something. And the sum would be QP that we'll use to choose an answer from. So let's perform the arithmetic. Calculator. Where is my gonculator? There we are. So 0.35 times 3.9 times 2 equals 2.73 cubic feet per second. And 0.65 times 3.9 times 4 equals 10.14 CFS. If we add those two together, plus 1, clear, 2.73 equals 12.87. Let's see what our potential answers are. The closest, without going over, is 13 cubic feet per second. So we'll go ahead and choose that and continue. All right. An alternative way to work this very problem, just while we're here, is to use a composite runoff coefficient, which is equal to the product, or the CA value of field 1 plus the CA value of field 2 divided by the area, the total area. So you would have 2 times 0.35 plus 4 times 0.65 divided by 2 plus 4 equals 0.55, and now we would do the peak is simply 0.55 times 3.9 inches per hour times 6 acres equals, we'll go ahead and do the arithmetic because we can, 0.55 times 3.9 times 6 equals 12.87. Same answer. Let's move to the next one. The rational formula runoff coefficient for a 950 foot by 600 foot property is 0.35. A storm occurs with an intensity of 4.5 inches per hour. The peak runoff from this property is most nearly, and select one, A, B, C, or D. So this particular problem, we already did the rational formula. Let's go back to our, so we still have Q equals CIA, but notice here the area is in acres, the intensity is in inches per hour, and it produces peak discharge in cubic feet per second. Our particular problem is not yet in area. We have area equals 950 times 600 square feet. Go ahead and perform the arithmetic. 950 times 600 equals 570,000 square feet. We need to convert square feet into acres. Of course, it doesn't have it. Okay, so we multiply an acre by 43,560 to get a square feet. So we have 1 acre is equal to 43,560 square feet. We'll now perform the indicated arithmetic. For 13.08 acres. We now can probably complete the problem. Let's return to the question. We have the runoff coefficient, we have the intensity, so QP equals runoff coefficient 0.35 times the intensity, 4.5 inches per hour, times the area, 13.08 acres. Perform the indicated arithmetic. So we have 13.08 times 4.5, I'm working from right to left now, times 0.35 equals 20.6 CFS, and our possible answers, I guess it's going to be A, number 21. Move on to the next one. Okay, our next problem. A watershed occupies a 70-acre site. So we have 70 acres. Of those, 45 acres of the site have been cleared and are used for pasture land with a runoff coefficient of 0.13. 3 acres are occupied by farm buildings, a house, and paved surfaces and have a runoff coefficient of 0.75. The remaining 22 acres are woodland with a runoff coefficient of 0.20. The total time to concentration for the watershed is 30 minutes. The 20-year storm is characterized by the intensity duration curve shown. Let's split off what problem information we can quickly. So we have 45 acres with a runoff coefficient 0.13. 3 acres with a runoff coefficient of 0.75, and 22 acres with a runoff coefficient of 0.20. We know that the time of concentration is told to us of 30 minutes, and we were given an intensity duration curve. Looks like that, and we want to go to the time of concentration value and then read the associated intensity. Okay, so we can probably approximate it just looking, but since we have the tools here on my computer, I'll go ahead and try to be sort of accurate. Get a screen capture. Open that up in graphic converter, my desktop. Let's get some drawing lines in here, and there, it should be small enough. So 30 minutes is between 20 and 40. So we draw a vertical line up like that, except that I want it more colorful. And the intersection is right there. So 10 is right there. It looks like 9 is my best guess, so I'm going to say that based on the chart, we have 9 inches per hour is my approximate intensity from that chart. And we're asked to find the peak runoff for the storm. So in this case, we could do this before and calculate the runoff for the 3 areas and add them together, but I think in this case it'd be much more convenient to produce a composite runoff coefficient. So C bar is equal to 0.13 times the 45 acres plus 0.75 times the 3 acres plus 0.20 times 22 acres Didn't know that was blocking things. All divided by 45 plus 3 plus 22. Now we'll perform the indicated arithmetic. 0.13 times 45 plus 0.75 times 3 plus 2 times 22 equals 12.5. Divide by 70, which is the 45 plus 3 is plus 22, for a composite of 0.178. Probably do 0.18, but there's our composite C value. Now we can apply the rational formula as per really. There we go. Q equals CIA. In this case, C is 0.178. Our intensity is 9 inches per hour. And our area is 70 acres. We'll perform the indicated arithmetic. Zero 0.178 times 9 times 70 equals 112.5. cubic feet per second. And we'll go back and look at our options, and the closest is 110. It's certainly not 50, it's not 240, it's closest to 110. So we'll move on. Oh. Let the server do its thing. Wow, that was annoying, wasn't it? All right, here's our next question. The table shown contains curve numbers based on land use and soil type. A watershed contains 10 acres of residential land of soil type B and 5 acres of grassland of soil type A. Here's the table of curve number values. So residential type A is 57, type B is 72, and grassland type A is 30, type B is 58. If the total precipitation depth is 11 inches, what will be the approximate runoff depth from the watershed? So here, let's look up curve number. I happen to know we're on the correct page, but there we go. So here's our formulas. We have the NRCS rainfall runoff equation, and that equation says that Q, which is the watershed runoff, is equal to the input depth, P, minus 0.2 times the storativity. It's the amount stored on the watershed, divided by P over 0.8 times the storage. The storativity is 1,000 divided by curve number minus 10. And the curve number, for what it's worth, is 1,000 over S plus 10. Now let's return to our problem. We have 10 acres Curve number, so we have 10 residential soil type B, so that's curve number 72. And we have 5 acres. Curve number, soil type A, 30. Like with the rational method, we could either compute each of the partial contributions and add them together, or use a composite curve number. I'm going to use a composite curve number. So the composite curve number is the curve number multiplied by 10 acres for the first partition, and the curve number 30 multiplied by 5 acres for the second partition, divided by the sum of the areas, 10 acres plus 5 acres. We'll now perform the indicated arithmetic. So 72 times 10 plus 30 times 5 equals 870, divided by 10 and 5 is 15, equals curve number 58. We're now going to substitute this value up into that formula to recover the value for storativity, and then we'll put that in these two locations here. So, storativity, or the storage, I don't believe I'm using the correct terminology, but close. 1,000 over 58 minus 10. We'll perform the indicated arithmetic. 1,000 divided by 58 minus 10, 7.24, probably good enough. And now we put Q is equal to P, which in our case is 11 inches. So we have 11 minus 0.2 times 7.24 squared divided by 11 plus 0.8 times 7.24, and we'll perform the indicated arithmetic. All right. Okay, first we'll do the numerator and then the denominator. So, 11 minus 0.2 times 7.24, and then I want to square that thing, divided by the quantity 11 plus 0.8 times 7.24, 5.43, and it's going to be in units of inches. And I guess 5.4 is the closest answer. Move on to the next page. Next question. A drainage basin covers an area of 2.4 acres. During a storm with sustained rainfall intensity of 0.6 inches per hour. The peak runoff from the basin is 320 gallons per minute. What is most nearly the runoff coefficient for the basin? If we return to our supplied reference, we'll find we're still in rational formula. So Q equals CIA. But now we recall that we have to deal with unit conversion. So we're given that the area is 2.4 acres. The intensity is 0.6 inches per hour. Q is equal to 320 gallons per minute. And C is the unknown value. But the rational formula is specific in that a product of intensity in inches per hour, area in acres, produces discharge in cubic feet per second, but we have it in gallons per minute. So we're now going to have to convert gallons per minute into cubic feet per second. If we return to our supplied reference, let's see what we can get. Okay, liters per second to gallons per minute. Okay, we're going to have to stick with should have a gallons to a cubic foot somewhere. There we go. Okay, so we want this in cubic feet per second. And this conversion factor says multiply a gallon by 0.134. And then we have 1 minute equals 60 seconds. And we'll get this into cubic feet per second. So 320 times 0.134 divided by 60 equals 0.714 feet cubed per second. And now we'll rearrange the equation and solve for C. C is equal to Q over I times A, which equals 0.714. Put that 6 in there, it seems important. Divided by 0.6 inches per hour and 2.4 acres. Divide by 0.6. Divide by 2.4. And it says that we have a runoff coefficient of 0.496. Let's look at our answer choices. Closest one we have is 0.5. And let's choose that and move on to the next problem. Okay, the next set of problems deal with hydraulics. So I'm going to pause the video capturing, do some editing, and then return to the video stream. Here's our next problem. So this is hydraulics. A model of a dam has been constructed so that the scale of the dam to the model is 15 to 1. That is, the real dam, I'm assuming this is geometric similarity, it's not clear by the problem statement, is 15 times bigger in its dimensions than the one. Next thing, similarity is based on Froude numbers, so this is probably dynamic similarity. At a certain point on the spillway of the model, the velocity is 5 meters per second. So we make a measure on the model, it's 5 meters per second, and we want to answer the question at the corresponding point on the spillway of the actual dam, the velocity would most nearly be A, B, C, or D. And this is a little more elaborate. Let's go ahead with similarity. S-I-M-I-L-A-R-I-T-Y. And we find the similitude. So in order to use a model to simulate conditions, the model must be geometrically, kinematically, and dynamically similar. To obtain dynamic similarity between two flow pictures, all the end of blah blah blah. And the one we're interested in, oh Nico, don't go chewing on the camera. Crazy beast. We're interested in this line right here, where the cursor is moving back and forth, where the Froude number of the prototype is equal to the Froude number of the model. So this is from page 117, Fluid Mechanics. And we simply have that the Froude number of the prototype, which will be the dam, is equal to the Froude number in the model. Notice the square brackets are implying that the dimensionless pi groups have that. And so now we have to go look up what a Froude number is. Froude number FR. And we now have that the Froude number, by definition, autofocus wasn't focused. So Froude number by definition is velocity over square root of g y sub h. And now we have what we need. We want to establish these two ratios. So velocity of the dam over root g y sub h dam has to equal velocity of the model over square root g y sub h model. And we're after the velocity of the dam. The question is, what is the velocity on the dam? So velocity of the dam equals velocity of the model root g y h model. Oh, you gonna help, Kat? Are you gonna help? Yeah. Why don't you go help by going right here? There you go. Velocity of the model, root g multiplied by g y sub h dam. Velocity of model, root g, those will cancel. Root y sub h dam, root y sub h model, and we know that the ratio y sub h dam the model is 15 to 1. We're told that. So this is v model, square root of 15 to 1. And we now can put in our numerical values. The model was 5 meters per second, square root of 15 over 1, and perform the indicated arithmetic. Take its square root, multiply that by 5, hit the equal sign, 19.36 meters per second. So we turn to our choices, and the closest answer is D. Next one, open channel, has a cross-sectional area of flow of half a meter squared, a hydraulic radius of 0.15 meters, and a roughness coefficient of 0.15. The slope of the hydraulic grade line needed to achieve a flow rate of 10 liters per second is most nearly A, B, C, or D. So here we're going to go with, let's search for open channel and see what there is to see. Oh, right there. That's not terribly useful, but turns out on this page we have Manning's equation. Focus is there. We have Manning's equation, which says that the discharge is equal to some constant. You can stay here, but you got to lay down. Returning to that, dealt with a cat issue. We're interested in Manning's equation for this particular problem, and we are on page NCEES, page 173, civil engineering. Okay, we have Manning's equation. Q equals K over N. This problem is stated in meters, so it's 1 over N A R sub H to the 2/3 power, S to the 1/2 power. The slope S is the slope of the hydraulic gradient. So our question, let's refresh the question. A is given, 0.5 meters squared. Hydraulic radius is given, 0.15 meters. N is given, 0.15. Q is given, 10 liters per second. This equation up here is going to assume everything is in cubic meters per second, so we'll have to make some adjustments for that. And S is equal to the unknown value. So 10 liters per second, there are 1,000 liters in 1 cubic meter. You get that from NCEES page 2 conversions. go look it up to be sure. Let's see. Of course not. Whoa, yep. Go to where I want it. Cubic meters is 1,000 liters. Okay, we'll use that page of Manning's equation, which is not 173. Cool, it's also page 111. I guess page 110. Nope, 111, fluid mechanics. Alright, so let's rearrange the equation. S to the 1/2 power is equal to Q times N divided by A R sub H to the 2/3. This equals, see, 10 over 1,000 is 1 in 100. 0.01 meters cubed per second times 0.15 is the roughness coefficient divided by 0.5 meters squared is the area, and 0.15 to the 2/3 power. And then we'll first perform that indicated arithmetic, and then we'll square the result to recover the slope. Okay, clear that. And 0.01 times 0.15 equals that. Store that in the memory. Clear. 0.15 is 2/3. 0.6667 equals that, times 0.5 equals that. We will invert it, multiply it, so it's in memory, to get a slope of 0.0. 0.0106 is the square root of the slope, and so the slope is 0.0106 squared, which equals 0.0001129. 1, 2, 3, 4. 1.129 times 10 to the minus 4th is the slope. Let's go see our options. And 1.129 closest is this one, 1.1 times 10 to the minus fourth. All right, welcome to our next problem. So in this problem, water flows through a converging fitting as shown and discharges freely to the atmosphere at the exit. Flow is incompressible, friction is negligible. The gauge pressure at the inlet, this end, is most nearly, and we're given some options A, B, C, or D. We're going to want to, we're going to need the continuity equation, and we're also going to need the energy equation. So the continuity equation is on page 109, Fluid Mechanics. And that equation is A1V1 equals A2V2, and we'll use it shortly. The energy equation is on page 110. And we're actually going to use the field equation version of it because we're told that friction is negligible. So we have P1 over gamma plus V1 squared over 2G plus Z1 equals P2 over gamma plus V2 squared over 2G plus Z2. So there's our two tools, and let's notice in our flow system first that at the inlet we know the diameter and we know the velocity. At the outlet we know the diameter and we know the pressure, and we're asked to find the pressure at the inlet. So we'll let 1 equal the inlet and 2 equals the outlet. With that in mind, we have P1 over gamma equals P2 over gamma plus V2 squared over 2G minus V1 squared over 2G plus Z2 minus Z1. In our particular problem, Z2 is equal to Z1, so that difference is equal to 0. P2 is equal to 0 gauge, 1 atmosphere, we're told that. And so what's left is P1 over gamma equals V2 squared over 2G minus V1 squared over 2G. So now we have to find the two velocities. We're told that V1 is equal to 1.2 meters per second. We know that A1 is equal to D1 times pi over 4, D1 squared times pi over 4. A2 equals D2 squared times pi over 4. And so let's apply continuity. D1 squared pi over 4 V1 equals D2 squared pi over 4 V2. 4's cancel, pi's cancel, and V2 equals D1 squared over D2 squared times V1, which equals D1 over D2 quantity squared times V1. D1 we're given is 150 millimeters. D2 is 75 millimeters, quantity squared times V1, and that produces 4 V1. So we'll substitute in the numbers. V1 is 1.2 meters per second. V2 is 4 times 1.2, which equals 4.8 meters per second. So now we have P1 over gamma equals 4.8 meters per second squared minus 1.2 meters per second squared. This is over 2g. This is over 2g. So P1 is equal to 4.8 meters per second squared over 2g minus 1.2 meters per second squared over 2g multiplied by rho g. Alright, let's put in the rest of the arithmetic. 4.8 squared over 2 times 9.8 minus 1.2 squared over 2 times 9.8. Rho is 1,000 kilograms per meter cubed times 9.8 meters per second squared. And so that'll be meters per squared per second squared, meters squared per second squared. There's meters per second squared, meters per second squared. Yeah, the units are going to work out, which is what I was concerned about. And so let's return to our prop. That's not what I wanted. That's scary. Okay. All right, let's clear that. So we have 4.8 x squared minus 1.2 x squared equals that. So all divided by 2 divided by 9.8 times 1, 2, 3 times 9.8, and we have 10,800 kilogram meters per second squared. 10800 kilogram meters per second squared, which is 10,800 pascals, which is 10.8 kilopascals. So now we'll return to our problems. Oh, the problem's right there. Bring that up to the front. And our choices are 10.2, 10.8, 11.3, and I'm going to go with B. Okay. We have the hydraulic radius of a 5-meter deep triangular channel with 1-to-1 side slope is most nearly. First we have to look up what a hydraulic radius is. Okay, hydraulic radius appears on page 111, and R sub h is equal to the area over the wetted perimeter. Of course, that particular example is for a completely full conduit. And here's a better variant of it, and that's the one we're going to use. They're both saying the same things. Okay, so now we need to figure out the area. And what we're given is a 1-to-1 side slope, which essentially, if that's the case, this is 45 degrees. told that that is 5 meters. So what we need to do is simply find that area and multiply it by 2. If this angle is 45 meters, then so is that angle. And so we know that this length, L cosine 45 equals 5. And once we can find the length, it'll be pretty trivial to get the areas as well as the wetted perimeter. Now, where that formula came from, it came from trigonometry. Whoa. So I'm using, in my case, R, and then theta is the angle. And so I have cosine is x over r, or in our case, r equals r cosine theta is equal to x. So now we have to first perform the intermediate arithmetic. Hopefully this is good. It does have cosines. So we're after L is equal to 5 over cosine 45. And let's see, I want to be in degrees. That looks about right. Okay, clear that. 5 divided by 45 cosine equals 7.071 meters. Now the area is 1/2 base times height. So we also know that L sine 45 equals this width. So 7.071 sine 45 equals W times 45 sine equals 5. Probably could have figured out it was equilateral triangle. No, it's not equilateral triangle. Okay, so 1/2 base times height is 1/2. Okay, so the base is 5, the height is 5. 5 times 5. And that takes care of one of them, but then there's 2 of those. So it's 25 meters squared. And our wetted perimeter is 2L, which equals 2 times 7.071. 7.071 times 2 is 14.142. And now we can calculate the hydraulic radius. Equals 25 meters squared over 14.142 meters. One point seven 1.76 meters. And our answer choices are the closest 1.8. Okay. Next one. Pipe carrying an incompressible fluid has a diameter of 100 millimeters at point 1 and a diameter of 50 millimeters at point 2. The velocity of the fluid at point 1 is 0.3 meters per second. What's the velocity at point 2? Okay, we've done one like this already. We want the continuity equation. CONTINUITY It really can't find it. Apparently spelling matters. This doesn't have spell check. Of course it doesn't. Alright, continuity equation simply says that A1 V1 equals A2 V2. So in this case, this will be very straightforward. A1 V1 equals A2 V2. A1 is equal to pi d1 squared over 4. A2 equals pi d2 squared over 4. And we're after velocity 2. So velocity 2 is equal to A1 over A2 times V1, which equals pi d1 squared over 4 over pi d1 squared over 4 times V1. Pi's cancel, 4's cancel, equals d1 over d2. Quantity squared times V1. In our case, we're told that d1 is 100 millimeters, and d2 is 50 millimeters. Quantity squared times V1. 100 over 50 is 2, 2 squared is 4, so we have 4V1. So finally we have V2 is equal to 4 times V1, which is 0.3 meters per second. No calculations required. That's 1.2 meters per second. And we're going to choose, in our case, our options are B. Alright, we're now moving into the next and final series of topics, groundwater. First question, water drains at a constant rate through a saturated soil column with a diameter of 1 foot and a height of 2 feet. The hydraulic head is maintained at 5 feet at the top of the column relative to some datum and 0.5 feet at the bottom of the column relative to the same datum. After 1 hour, 100 cubic inches of water has drained through the column. What's the hydraulic conductivity of the soil? We will find that if we search for hydraulic conductivity, it gets us to page 152 in the civil engineering section. Of the NCES supplied reference. And in that, it says that the hydraulic conductivity for a constant head permeameter is K is equal to Q divided by IA times the elapsed time, where I is the change in head over the change in length. Q is a volume. A is cross-sectional area. So these are a constant head permeameter like you had in your soil mechanics classes. Let's draw ourselves a sketch because it's a little easier to see what's going on. So here's our soil column. It's 2 feet tall. base diameter of 1 foot. The head here is 5 feet above some datum. And the head down here is 0.5 feet above the same datum. So our hydraulic gradient, change in head is 5 feet minus 0.5 feet. Change in length is over 2 feet. This is 4.5 feet over 2 feet, which equals, bring that up on the calculator, 5 minus 0.5 equals that divided by 2, which is 2.25. 2.25 is the gradient. Q is 100 inches cubed, but if we look at the answer units, we want these to get into feet per second. So there are 12 inches in 1 foot. So we'll convert 100 cubic inches into cubic feet by making that necessary arithmetic. We divide by 12 3 times. 100 divide by 12, divide by 12, divide by 12, 0.05787 feet cubed. That should be enough significant digits. And we have a lapse time of 1 hour, but we want it in seconds. So there are 1 hour is equal to 60 minutes. 1 minute is equal to 60 seconds. So that's 3,600 seconds. Now we want our area in feet squared. We have pi 1 foot squared over 4. Pi times 1 divided by 4 equals 0.7854 feet squared. And now I believe we have all the pieces we need to express the result in feet per second. So K is equal to 0.05787 cubic feet over 2.25 is the gradient. Area is 0.7854 feet squared, and the time is 3,600 seconds. Okay, clear that, and we'll do the arithmetic. 0.05787 divide by 2.25 divide by 0.7854 divide by 3,600 this equals 0.100000909 1 2 3 4 5 6 9.09 times 10 to the minus 6 feet per second. And our closest answer is 9.1 times 10 to the minus 6 feet per second. All right. Alright, our next problem. Okay, this doesn't need much of a lookup, but let's just look up Darcy's law. Has to do with porous media. So let's look at our choices. Open channels, nope. Pipes, nope. Pitot tubes, nope. Porous media, yeah. V8 hinges, no. So the best answer here is porous media. Alright, here we have another actual constant head permeameter test. Okay, soil sample with permeability of 5 times 10 to the minus 6 inches per second. We tested using the pipe setup shown. The pipe diameter is 2 inches. The 10-inch head differential will be maintained. What's the volumetric flow rate? So here we're going to write Darcy's law actually in this fashion. Q equals, we are on NCEES page, pretty sure this is 171. It is 171 civil engineering. Q is equal to minus KA dH dx, which would be KA change in head over change in length in the flow path direction. And since I'm a cheater, I'm going to do that. Let's return to our problem. Okay, so our change in head is 10 inches. Our flow path length is 20 inches. So delta H over delta L equals 10 over 20 is equals 0.5. Cross-sectional area is pi 2 inches squared over 4, which equals pi, 2 is 4, pi inches squared. Weird unit. And our hydraulic conductivity is 5 times 10 to the minus 6 inches per second. So Q is equal to 5 times 10 to the minus 6 inches per second times pi inches squared times 0.5, which equals calculator, clear everything. Let's calculate. 5E6 minus times pi times 0.5 equals 0.1212378 1, 2, 3, 4, 5, 6. 7.85 times 10 to the minus 6 inches cubed per second. And our best answer is C, 7.9 times 10 to the minus 6th. Move on to the next page. Aquifer has a thickness of 52 feet, transmissivity of 650 feet per day. What's the most likely hydraulic conductivity aquifer? That happens to be on the same page. NCEES, page 171, civil engineering. And it says the transmissivity T is equal to the hydraulic conductivity times the thickness. Product hydraulic conductivity and thickness is the transmissivity. That is simply a definition. We will apply that definition and find the answer. So we know that the transmissivity is given as, well, K is equal to T divided by B, which in our case is 650 feet squared per day, divided by the thickness, which is 52 feet, and the result of that rather difficult calculation there, 650 divided by 52 equals 12.5 feet per day. And we will go with 13, that's the closest, and move on. All right, the results of a pumping test from a homogeneous unconfined aquifer are shown. At the time of the test, pumping had continued long enough for the well discharge to become steady. The pumping test results are shown in the table: 20 gallons a second, 1.5 foot well diameter or borehole diameter. The radius of influence is 900 feet. At the radius of influence, the aquifer depth is 135 feet. The well drawdown is 11 feet. Find the hydraulic conductivity. Yet again, we're on the same page, but let's pretend that we didn't know that. We look at drawdown, and we have an unconfined versus a confined. In our problem statement, we're told it is unconfined, so we're going to use the Dupuy formula up here. And the Dupuy formula says that Q is equal to pi times the hydraulic conductivity times the square of the head at position 2 minus the square of the head at position 1 divided by the natural logarithm of radius 2 over radius 1. And so we want to take that equation and we want to rearrange it to solve for the unknown value of K. First thing we're going to do is we'll go ahead and write that equation. Q equals pi K H2 squared minus H1 squared over natural log R2 over R1, and this is NCEES, page 171, Civil Engineering. Let's rearrange this for K. Q times the natural log R2 over R1 equals pi K H2 squared minus H1 squared. Q log R2 over R1 over pi H2 squared minus H1 squared equals K. Now we're given Q in this problem of 20 gallons a second. We want to convert that into feet squared per second. Feet cubed per gallon. So we'll go here and go back to conversions. We have multiply gallons by 0.134 to get cubic feet. Perform the arithmetic. 20 times 0.134 equals 2.68. Now I believe we have everything in the correct units. So let's go ahead and perform the arithmetic. We have 2.68 feet cubed per second. Natural log R2 is 135. R1 is the radius of the well, diameter 1.5 feet. Half of 1.5 is 0.75 feet. divided by pi. H2 squared is, this is wrong, this is 900 feet. This is 135 feet squared minus, draw down at the well, it's going to be 135 minus 11. Drawdown is this distance, and we want to know what the head is. So this is going to be 135 minus 11 squared equals K. Let's work on that denominator first. 135 minus 11 is 124. So this is 2.68 natural log 900 over 0.75 over pi times 135 squared minus 124 squared. Now we'll perform the indicator arithmetic. I think it's easier. Okay, clear everything. 900 divide by 0.75. Take the natural log of that. Multiply that by 2.68. Clear the memory, add it to the memory. Oh, clear the memory. Okay, so the numerator is 19. Add that to memory. And then 135 x squared minus 124 x squared equals that, times pi equals that. And we want to invert it, times memory recall equals 0.00212 feet per second, 23, which is 2.12 times 10 to the minus 3 feet per second. And our closest answer, without going over, is B. All right. So now we've answered all 15 questions, and you've seen the gory details of how to obtain the answers. Let's submit all those and finish. And we got 15 out of 15. Now, it took 2 hours and 34 minutes to go through all that. That's because there was a substantial explanation. Now, on an actual exam, if you were working 4 minutes a problem, that would have been 1 hour. So that's too slow. You probably need to get this to half an hour. However, with practice and not having to explain it, your speed can go considerably higher. Here's each of the questions repeated. And all of this will be online in the video, and the worked answers at some point will be scanned as PDF files. And that concludes this set of lessons. I had a little fun here because flow through V8 engines, motorhead kind of thing. And that completes this review.